All right, guys. So I know that we had a little trouble with turning position versus time graphs into velocity versus time graphs. So we're going to do a little bit more practice with those. All right, so we have to know these before we move on to acceleration, like whenever we add acceleration graphs into it. So at this time, we are only dealing with constant velocity. Okay, so constant velocity means that we are not going faster, we are not going slower, and we're not changing direction. All right, so for these, we're going to have graphs that are super, super simple, but we need to know what each of those symbols mean on a graph, or not symbols, but each of those segments mean on a graph so that we can know those before we move on to acceleration. All right, so for a position versus time graph, all right, the two things that we need to know are what the slope represents and what that y-intercept represents. So I think I've said this about 5,000 times, so you should all know it. But the slope of a position versus time graph is the velocity of the object. Now, we don't talk about the y-intercept quite as much, but we have mentioned it before. The y-intercept for a position versus time graph is where the object starts, so it's starting position. Okay, whenever we turn those position versus time graphs into velocity versus time graphs, this is just a little intro into what we're going to get into next. The slope of a velocity versus time graph is going to be the object's acceleration. All right, now, even though we're just dealing with constant velocity, that doesn't mean that we're not looking at acceleration yet. That just means that the acceleration is going to be 0. Okay, and whenever we are looking at the y-intercept, that just means, so if the y-intercept is the starting position on a position versus time graph, the y-intercept for a velocity versus time graph is going to be its starting velocity. Okay. All right, so what we are going to do is I have 5 different scenarios, just 5. It's nothing big. Stop complaining. Stop rolling your eyes. All right, so I have 5 different scenarios, and I want you to create position versus time graphs and turn them into velocity versus time graphs. So this is exactly what we did in our walking directions lab. I gave you the scenario and you walked it out. So instead of walking it out, we're just going to go straight from the scenario to the graphs. All right, so the first one, Maria is walking at a constant velocity of 6 meters per second for 5 seconds. All right, that's our first segment of motion. Then she runs at a constant velocity of 10 meters per second for the next 5 seconds. All right, so we should be starting to think about how these graphs are going to look, how many segments there are going to be, what direction we have. But notice that I did not give you a specific direction. So remember, if I do not give you a specific direction, we always assume it's going in the positive direction. All right, so let's create our position versus time graph first. All right, so we know that time is going to go on our x-axis, measured in seconds, and because our velocity is measured in meters per second, we know that our position is going to be measured in meters. Always label your axes and give me a title. We just have position versus time again. Now, for this one, I gave you the seconds. All right, so we know that we have up to 10 seconds. So let's go ahead and mark those. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Go ahead and label those. This is going to take me a second. Bear with me. Come 9, and 10. All right, now for position, I did not give you the position, and technically we can use our velocity equation to work backwards and find out what position is changing per second, but I'm not going to make you do that on this one. This is just trying to get the shape of these graphs. All right, so the first thing that I want you to notice is we have a constant velocity. So you should know that a constant velocity on a position versus time graph is a straight diagonal line. All right, so this straight diagonal line is at 6 meters per second. Okay, so for the first 5 seconds. So we're just going to draw a straight diagonal line for that first 5 seconds. That's going to represent our first segment of motion. Now, after that first segment of motion, she increases her speed to another constant velocity, but this time it's at 10 meters per second. So we're still going to have a straight diagonal line, but this one is just going to be a little bit steeper because it's going faster. So we're going to go where we ended, and it will just be a little bit steeper until that 10 seconds. So both of these are straight diagonal lines. That tells us that we have constant velocity, and both of them have positive slopes, which means they're both going in the positive direction. All right, they never stop. There are no horizontal lines, so we should know that this is what this looks like. So 2 different lines, 2 different slopes. All right, so if we turn this into a velocity versus time graph, a lot of you were asking if you have to draw the T, the full T, every single time. You do not, all right? In this case, they're both going in the positive direction, so technically we do not have to have that bottom T, the bottom of the T. So if you want to draw the T every single time, be my guest, but you do not have to. But on the x-axis is still time. Your time is always going to be the same. So your x-axis is going to be the same for your position versus time graph, turning it into your velocity versus time graph, turning it into your acceleration versus time graph. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, and I had one more. 4, 5, 6, 7, 8, 9, 10, and an 11. All right, so we know that velocity is on our y-axis, measured in meters per second. Now, on that T, at the origin, we know that our velocity is 0. Everything above the origin is going to be positive, and everything below the origin is going to be negative. All right, that positive, again, means that it's going in the positive direction. The negative means it's going in the negative direction. We do not have anything going in the negative direction, so we will not have anything below that 0, below the x-axis. All right, now for this one, I did give you velocities, so we can put numbers on our y-axis here. So we have 6 and 10, so I'm going to go up by 2. So we have 2, 4, 6, 8, 10, and 12. All right, so we're just going to label those. Okay. So we know that the straight diagonal lines mean constant velocity. So that, whenever we're turning it into a velocity versus time graph, is shown as a straight horizontal line. But we know the first one is going to be at 6 meters per second for 5 seconds. So we're going to start at 6. And it's going to be a straight horizontal line until you get to 5 seconds. And then after that 5 seconds, it changes velocity. So we're not going to start back at the y-intercept. We're going to start where we left off at 5 seconds. And we're going to jump up to 10 meters per second. Again, that is a constant velocity. So that is shown with a straight horizontal line. Now, we do not have to connect these, but if we want to, remember that that is shown by a vertical dotted line. All right, and then that's it. That is our position versus time graph for this motion, turning into a velocity versus time graph for this motion. Notice they don't look similar, but they are showing the same thing. They're showing the same motion. All right, so let's move on to our second scenario. So think of Thanksgiving. All right, so we are at a Thanksgiving meal. Your mom walks 5 meters to the kitchen at a velocity of 2 meters per second, pauses by the refrigerator for 3 seconds, and then walks back with a plate full of potato salad at a velocity of 1 meter per second. All right, so the first thing that you should know, notice is that we have 3 different segments of motion. All right, so the first one is she's leaving, say, the dining room. The dining room is going to be our origin, and she is walking to the kitchen at a velocity of 2 meters per second. After that, she pauses by the refrigerator for 3 seconds. And then after that, she's going to walk back to the dining room at a velocity of 1 meter per second. So we have 3 different segments of motion happening here. All right, so we are going to draw our position versus time graph. It's a normal L graph again. Time is on the x-axis, position is on the y-axis. Position is going to be measured in meters, again, because our velocities are found in meters per second. And we know the slope of a position versus time graph is velocity. Don't forget to title it position versus time up here. Ooh, I forgot to title our velocity versus time graph over here. So do not forget that, like I did, sorry. And underline. All right. So if we are using these, I didn't give you really a time for this. Again, these are just sketches. I'm not looking for exact things, or exact numbers, unless I specifically give you these exact numbers. So we know that she starts from the origin, which is our dining room, and goes to the kitchen at a velocity of 2 meters per second. Well, we're going to assume that that's a constant velocity. All right. So she's going to move forward to, let's hope that, yes. So to the refrigerator at 2 meters per second, constant velocity. Easy peasy. All right, so our second segment is she pauses by the refrigerator for 3 seconds. Well, what does that mean? If she pauses, that means that she is looking in the refrigerator, digging in the refrigerator, but not changing her position. So she's not moving, which is shown by a straight horizontal line for those 3 seconds. Now we know that she walks back. She walks back to where she came from. So at this point, she's going to turn back around and go towards the dining room again, which is our origin. All right, so we know that she's walking back. She's walking a little bit slower because she doesn't want to spill the potato salad anywhere. So it's another constant velocity, another straight diagonal line. This time it's going to have a negative slope. And because it's going slower, it's going to be a less steep slope, which is kind of what we see right here. All right, what if we do that? Yes. Okay, I love that it connects these for me. All right, so that is what our position versus time graph would look like. All right, so let's turn that into a velocity versus time graph. Now, if you're asking, should I draw the full T this time? The answer is yes. Why should we draw the full T? Well, that's because we have things going in the positive direction and the negative direction. So we're going to use this little white line as our origin. There we go. All right, time is still on the x-axis. We have velocity on the y-axis measured in meters per second. We are going to title it, I'm not going to forget this time, velocity versus time. Okay, now for these, we know that the velocity at the origin, where that x-axis meets the y-axis, is 0. Everything above it is positive, everything below it is negative. So that means everything above it having a positive velocity means that you're going in the positive direction. Having a negative velocity means you're going in the negative direction. All right, so I did give you the velocities for this. I gave you 2 and 1. So we need to make sure that both of our positive axis and our negative axis are still going to have the same number. So for me, because it's so small, I would just go up by 0.5. So we're going to have plus 0.5 plus 1, plus 1.5 plus 2. And then we're going to do that same thing down here, negative 0.5. Negative 1, negative 1.5, and negative 2. All right, so now we can actually draw our line. So we know the first one's going to be positive. It's going in, it's going in the positive direction. So it's going to be above the x-axis at 2. So for the first little bit, pause, hang on. We're going to do that. Like, oh, no. Sorry, y'all. Give me a second. This back to where it was. There we go. All right, I'm going to put the 2 right there. Sorry, it was just going to go into the title, so I just had to fix that. So I do apologize. All right, so our first little segment is just going to be a straight horizontal at 2 for the first little bit. Now we know once she got to the refrigerator, she stopped. So it's a straight horizontal line. So what is the slope of a straight horizontal line? Hopefully you are saying 0. That means she was not moving. Her velocity was 0. Now, after she left the refrigerator, she headed back to the dining room, back to the origin. That's in the negative direction. And it's going to be, I told you, a constant velocity of that negative 1. All right, so we're going to see a straight horizontal line at negative 1. Okay, so that's what our velocity versus time graph should look like. Again, you do not have to connect them, but if you want to, those straight vertical dotted lines are there for you. Okay. All right. Now this third one, I love this third one. It's one of my favorites. All right. I don't know why it's my favorite, so don't judge me. It's just fun to make. All right. So for this one, at track practice, the coach makes team members run back and forth between 2 different lines 3 different times. Okay. So we have 3 things happening. They're going to a line, coming back, going to a line, coming back, going to a line, coming back. All right, so I want to sketch a position versus time graph for this and then turn it into a velocity versus time graph. All right, so let's draw our position graph. Okay, let's just make it a little bit longer. All right, so time is on our x-axis, measured in seconds. I really didn't give you any numbers for this, so I guess you could do it in any units that you wanted to, but let's just stick with meters per second. So position is in meters, time is in seconds. So title it position versus time. Okay, now, again, they're going back and forth between 2 different lines. So they're going from, say, the origin to a line, going back to the origin, to another line again, going back to the origin, to the line again, and then running back to the origin. All right, so what that would look like is they're moving in the positive direction and then coming back to the origin, which is the negative direction. Moving to a positive direction, that line that's somewhere across the field, and then coming back to the origin. Going back to that line, positive direction, coming back to the origin, which is a negative direction. So that would look like 3. Going to the line, whatever line it is, coming back to the origin. Going to whatever line that is, coming back to the origin. Going to that same line, coming back to the origin. Now, if I were measuring these, all of these would be the same. They'd all have the same slope, again, like not the same direction, but the same slope. All right, so what we are looking at is constant velocity, just different directions. All right, so if I want to draw a velocity versus time graph for this, yes, I would draw the whole T because I have both positive and negative. So time is still measured in seconds. Remember, your time axis is identical for position versus time, to velocity versus time, to acceleration versus time. Our velocity is going to be measured in meters per second. We're going to title it Velocity versus Time, just in case I forget again. And we know that the velocity at the origin, so where the x-axis meets the y-axis, is 0. Everything above it is positive. Everything below it is negative. Now, I did not give you any numbers for this whatsoever. All right, so if you just wanted to make yours up, that's fine. For me, I'm just going to estimate it. All right, so we know that for the first part, so we technically, let's see, let's use different colors. All right, so we have positive direction, constant velocity. All right, so that's going to look like this. We're going to have it up top for a little bit. And then they're going to come back. All right, so they're going to come back to the origin. That's a negative slope, which means it's in the negative direction. All right, so it's going to be below 0. Now, we know they're going about the same velocity going as they are coming. So we're going to do it as close as we can to have the same distance away from 0. Well, let me make that just a little bit shorter. Okay, then once again, she's going in the positive direction. So we have another line. And then we're changing to negative direction. So where we left off. Da, 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 da. And another positive direction. So we're going to go back up here. They're getting smaller. They're not supposed to be smaller, but I can't fit. And then last, they're going in the negative direction. So we would go right down here until the very end. Okay, so we have 6 different segments because you have 1, 2, 3, 4, 5, 6. 3 are in the positive, 3 are in the negative. So this is what that velocity versus time graph would look like. All right, see, it's just so much fun to make. Y'all made fun of me. I know you did. But it is just so much fun to make. All right, so for our fourth one, we're so close, y'all. Getting closer. A car is driving down the road at 5 miles per hour. Sorry, not 5, 55 miles per hour. But then it gets a flat tire and then moves at another constant velocity of 35 miles per hour. So if I wanted to sketch this position versus time graph, let's go ahead and set it up. So we have time on the x-axis measured in seconds. I did not give you specific times. Ooh, I just noticed a mistake on my part. So notice that our unit for our velocity is in miles per hour. So that tells us that our time is not in seconds, it's going to be in hours. Don't be like me, pay attention to those units. And then that means that our position is going to be measured in miles. All right, we're going to label it position versus time. Okay, now I have 2 different segments on here. I have a constant velocity of 55 miles per hour turning straight into a constant velocity of 35 miles per hour. So hopefully you've gotten the idea. Constant velocity is symbolized with a straight diagonal line. Both of these are going in the positive direction. I didn't tell you that it turned around. I didn't really give you a direction at all, so we assume that it's going in the positive direction. All right, so we know that we're going to have 2 straight diagonal lines going in the positive direction. So what's going to be the difference? How are we going to tell? What's the 55 mile per hour one look like from the 35 miles per hour one? I'm so glad that you just asked. So we've seen it in our notes. We've seen it in our labs. We know that the difference between a faster velocity and a slower velocity is the steepness of the line, the steepness of the slope. So if we're starting at a faster velocity, then our first line is going to be steeper, followed by a second line that's going to be not so steep. So you can see we have 2 straight diagonal lines. That tells us constant velocity. They both have positive slopes. That tells us they're both in the positive direction. But the first one, is steeper than the second one, which is exactly what we see here. Okay, So let's turn this into a velocity versus time graph. We technically do not have to draw the whole T. I think I'm just going to, like just that little part down there. All right, so our time is always on our x-axis. Time is still measured in hours. This time our velocity is measured in miles per hour. Okay, so we need to make sure that we check those. Velocity versus time graph is our title. Okay, now what is this going to look like on a velocity versus time graph? All right, so we have two constant velocities. So we know that that's going to be two straight horizontal lines. They're going to be above zero. So our origin is zero. Everything above zero is a plus. All right, now I did give you our velocity, so we do need to write numbers on our scale for our y-axis. All right, we have 35 and 55. For me, because this is so small, I'm just going to go up by tens. So we'll have 10, 20, 30, 40, 50, 60. All right, so it's a positive 10, positive 20, positive 30, positive 40, positive 50, positive 60. All right, now we know for the first part, however long that is, there's a constant velocity of 55 miles per hour. So we're going to start it off with that straight horizontal line at 55. And then we know after it gets that flat tire, it's going to go down here and have a constant velocity of 35 miles per hour. So that's what that velocity versus time graph would look like. Okay, easy peasy. All right, now our last one. Yay! Shouts of joy. All right, so we have our last scenario. A bullet is fired from a gun and travels 1,000 meters in 1 single second before hitting a solid target. Now, why do you think I would specify that it hit a solid target? What do you think is going to happen after it hits that target? It's going to stop, right? So it's going to travel really, really fast, 1,000 meters in 1 second, and then it's going to just come to a stop. All right, so let's see what that looks like on a position versus time graph. All right, so we have our position versus time. I know you're getting tired of writing this, but we've got to do it. So we have time measured in seconds, position measured in meters, title, position versus time, all the things. They're tedious, but they are necessary. All right, so, I just gave you 1 second, so we can really just do 1, 2, 3, 4, 5, 6, all right, or however long you have on your time axis. All right, now really the only thing that I gave you was that it traveled 1,000 meters in 1 second. So I'm just going to put, there's not really a good scale for that. I'm just going to put 1,000 meters up here. So if it traveled 1,000 meters in 1 second, we are going to assume it was going in the positive direction and that it was constant velocity. So we would have a straight, nope, I'm doing the wrong one. My bad. All right, it would travel from the origin to 1,000 meters in that 1 second. Bam. Super steep line. And then as soon as it hits that target, we know it stops. So that tells us that we have a straight horizontal line after that. Okay, so we have two different segments. So how does that interpret into a velocity versus time graph? We're going to have two segments there also. All right, so we have time on the bottom, still measured in seconds. We're going to do 1, 2, 3, 4, 5, 6. Dang it, I did a little bit longer. 1, 2, 3, 4, 5, 6, and 7. All right, now for this one, our velocity, which is on the y-axis, measured in meters per second. Again, I really only gave you that it traveled that 1,000 meters in 1 second. So if we divide that, then that's going to be 1,000 meters per second. So I'm just going to put that up there kind of like I did earlier. So we're just going to have 1,000 meters per second. So for that first second, it's going to have that straight horizontal line at 1,000 meters per second. For the rest of the time, after it stops, that horizontal line means that there's no slope, which means there is no velocity. The speed of an object at rest is 0. So the rest of our line is going to be a straight horizontal line at 0. Okay. All right, so I hope this helps you understand it a little bit better. But if you're still having trouble, please, please, please let me know. We can get some extra practice problems, do extra work, because this is going to be a huge part of this, not only this next test, but this whole first semester. So I hope this helps. Again, if you have any questions, let me know.